Hey guys, in this video I'll show you chemical reactions with the heaviest gas in the world, tungsten hexafluoride. In the comments under a video about its physical properties, I often came across comments mentioning that uranium hexafluoride is heavier than tungsten hexafluoride. Yes, it's true, but the physical properties of a substance are usually measured under normal or standard conditions, and uranium hexafluoride turns into a gas only at temperatures above 56 degrees. This is a reactive gas. In humid air, this gas smokes strongly, forming hydrogen fluoride and tungsten oxyfluorides. So I open the valve and gas begins to come out of the cylinder. Look, as soon as the gas comes into contact with air, it instantly hydrolyzes, forming white clouds of tungsten oxyfluorides and hydrofluoric acid. If we direct a stream of tungsten hexafluoride to a solution of lead nitrate, we'll see the formation of white, slightly soluble lead fluoride. This reaction proves the formation of hydrofluoric acid upon contact of tungsten hexafluoride with water or moisture. I showed the production of tungsten from this gas by deposition onto hot silicon and by reduction with hydrogen in previous videos. Today there will be some more chemical reactions with it. On Wikipedia you can read that on contact with water, tungsten hexafluoride gives hydrogen fluoride and tungsten oxyfluorides, eventually forming tungsten trioxide. This is what it looks like. At first nothing happens, but after a while, on the walls of a test tube we can already notice a yellow coating of tungsten trioxide and the precipitation of tungstic acid, which subsequently fills the entire test tube. The halide exchange reaction can be observed if tungsten hexafluoride is bubbled through titanium tetrachloride. The transparent liquid turns dark purple due to the formation of solid tungsten hexachloride and titanium trifluorochloride, the crystals of which you can now see on the glass tube. Thus, a solution of tin dichloride, not even when bubbling, but simply upon contact with tungsten hexafluoride vapors, turns bright blue due to the dissolution of tungsten compounds in it in intermediate oxidation states. If tungsten hexafluoride vapors come into contact with reducing agents, then we can observe a formation of tungsten blue. These are tungsten compounds in the oxidation state from +4 to +6, an analog of molybdenum blue. Alkali metal borohydrides, which are powerful reducing agents, also turn blue when in contact with gaseous tungsten hexafluoride, and the most reactive, lithium borohydride, ignites upon contact with it. In slow-mo you can clearly see how tungsten hexafluoride vapor is reduced upon contact with lithium borohydride and turns bright blue. This is sodium fluoride. I weighed out 7 grams of sodium fluoride, placed it in a quartz tube and heated it with tungsten hexafluoride vapor. The fact is that when heated, sodium fluoride is capable of absorbing tungsten hexafluoride to form double fluoride, which upon subsequent heating will decompose into the original substances. After cooling, the mass of sodium fluoride increased noticeably. If we continue to heat the resulting complex, it will decompose into sodium fluoride and tungsten hexafluoride. Tungsten hexafluoride forms differently colored adducts with organic substances. For example, with benzene it's red, with toluene it's dark purple. With acetone it's orange, with diethyl ether it's green. Here I directed a stream of tungsten hexafluoride onto the burning magnesium. What do you think is formed in this reaction? Write in the comments. Tungsten hexafluoride reacts vigorously with ammonia to form a brown solid, which is tungsten hexafluoride hexaammonia. Now I'll carry out the same reaction in a glass tube so that you can make sure that the resulting substance is solid and not gaseous. In humid air, it also gradually turns blue. For our next experiment, we'll need what you see on the screen. So this is pyrrolidone. Let's put it aside. We'll need a foam cover into which we'll fill with liquid nitrogen. Now, using liquid nitrogen, we can easily convert the heaviest gas into a liquid and solid state. To do this, I'll pass tungsten hexafluoride into a U-shaped tube, the other end of which will be plugged with a calcium chloride tube to protect it from moisture. I will place the U-shaped tube itself in liquid nitrogen. After some time, a snow-white mass forms in the tube. This is solid tungsten hexafluoride. At room temperature, it gradually melts and forms liquid tungsten hexafluoride. This is what solid tungsten hexafluoride looks like. At temperatures above 2 degrees, solid tungsten hexafluoride begins to melt. It is in the form of this transparent liquid that tungsten hexafluoride exists at a temperature of 2 to 17 degrees. I prepared liquid tungsten hexafluoride to demonstrate to you two chemical reactions with liquid ammonia and anhydrous hydrazine. Look how tungsten hexafluoride boils and the calcium chloride tube is gradually coated with tungstic acid. So now I'll add liquid tungsten hexafluoride to liquid ammonia, and let's see the difference with a previously carried out reaction of gaseous substances. After the heavy plumes of brown smoke have cleared, a small amount of tungsten hexafluoride hexammonia will remain in the reaction cup. If we add water, the color will turn purple. It is known that Anhydrous Hydrazine reacts very actively with transition metal halides, and I have already had several such reactions. Here is the reaction of liquid tungsten hexafluoride with Anhydrous Hydrazine. I didn't find a description of this reaction anywhere in the articles. Write in the comments what this black smoke could be. This white solid is the simplest molecular boron nitrogen hydride compound. If tungsten hexafluoride reacts actively with ammonia, then it's logical to assume that borane-ammonia complex will react with it even more actively. Yes, chemical intuition did not disappoint. First we saw tungsten blue again, followed by the ignition of borazane. If you direct a stream of tungsten hexafluoride at lithium aluminum hydride, it will also ignite. But here the ignition most likely occurs due to contact with hydrofluoric acid formed in the humid air. Thanks for watching, guys. As always, I would like to thank my patrons, because thanks to their support I'm able to create my chemical videos with such unique reactions. Your support gives me more flexibility in choosing chemicals and filming equipment, which in turn will allow me to continue creating chemical content. I hope you enjoyed it. See you in the next video.